all real numbers. You could put your finger on it, drag it across. You'll never have to lift your finger up, hence continuous. Discrete, it jumps from whole numbers or integers, and so you would have to put your finger on a point, pick it up, put it on another point, and another, and another. And then one-to-one function, mathematical definition, no two elements of the domain map to the same element of the range, essentially, so there's only one y for any given x value. So you'll see that when we look at the maps, it's pretty clear as to what meets the definition of one-to-one and what does not. So let's take a look at a couple examples. So domain and range. Should have a familiarity with domain and range, and we should know that our x values are our domain, that is our input, and we can describe them using these fancy brackets, and we would just list them in order. So numeric order, and we see we have 1, 2, 3, 4, and 5. And then the range pertains to our y values, our output, our dependent variable. And again, we would list them in order, 11, 12, 13. And then notice now that we've got 1, 2, 3 13s, 3 of the same values. We're not going to list that 3 times. We've already described it in here within the range, identifying 13 as a part of that set. And so we only list it once. So duplicated values are only listed. The dependent, the output, the y values, 0, 1, okay? Hopefully you got the same answer here. The one thing to be careful of is the range here again. Remember, we're going to list numerical order from low to high, and so you've got to put these in that order when you list it. Any questions on that part, be sure to bring them to class, and we will address them. Let's take a look at reasonableness, or identifying a reasonable domain and range. So these are problems that we just kind of want to think about what makes sense. Oftentimes, if we were talking about some sort of linear function here, right? So if I had an x and a y axis and I graph some line, a function on it, this is continuous, extending in opposite directions forever and ever and ever. Well, given context like these problems here, A and B, that doesn't necessarily make sense. Okay, in example A, where we have a hose that fills 10,000 gallon swimming pool at a rate of 10 gallons per minute, what makes sense? So if we're talking about the domain is your input, your independent variable, and so we're, in this case, literally talking about what we are putting into the pool, this water, and the time. Time is almost universally always domain. It doesn't run backwards, it doesn't slow down, it is always a constant rate. We'll say range here. And so we're talking about the time it takes to fill this pool with that water. So your x value, which would be linked to time here. So we can't have negative time, so we know it's not going to go, say, to the left of the y-axis over in this direction into the second or third quadrant. It's going to be in the first quadrant here. So it's going to have to be greater than or equal to, say, 0 time, again, because we can't go negative. And then it's going to be less than whatever time it takes to fill. Okay. And if asked, we could continue to proceed to kind of figure that out. We could divide by 10 gallons per minute to figure out how many minutes or how many hours that's going to take. But ultimately, what we're trying to do here is just determine what is reasonable. So this is not going to go to infinity in time. Okay, at some point it will reach its capacity, and then it no longer makes sense to identify possible domain values for that. So again, the domain of time here is just something between 0 and however long it takes to fill. That's what's reasonable for this situation. And then the range is going to be the gallons in the pool. And so again, you've got something that is greater than or equal to 0. So this would be the water or the gallons in the pool, and then less than or equal to the maximum, which is given to us there, 10,000. Okay, let's look at example B. Do that over here. So we have domain. And in this case, a restaurant needs to order chairs for its tables. One table can accommodate 4 chairs. So I have a table, and then I need 4 chairs for it. So we're going to have tables be our inputs, are independent, and the chairs depends upon how many tables you have. So this again, something that is kind of restricted by that 0 value. I can't have negative tables, so it's greater than or equal to 0, but then less than or equal to however many tables, we'll just say number of tables, the restaurant can accommodate. Nothing in here is given about the size of the restaurant. It's not really important. It could be a very large restaurant. It could be small. So I don't know how many tables, but certainly something like infinite amount of tables or 2,000 tables probably doesn't make a lot of sense. That's going to be kind of an upper limit of however many tables the restaurant can accommodate. And then the range. Okay, so this would be the number of chairs. And then this one kind of falls a little bit differently because we have a value. So every table takes 4 chairs. So if we're talking about this, I could have conceivably 0 chairs. Doesn't make a ton of sense, but I could just decide that my restaurant's not going to have tables. And then they're going to come every 4 after that. And then we'll just use 3 dots after that to imply that that pattern continues. So we can do something like that to identify the range. It's 0, 4, 8, 12. Based on the number of tables I have, I'm going to have an additional 4 every time. Okay, let's take a look at another example here in number 5. So again, this is off of the prior problems. We're asked to identify whether or not this is continuous or discrete in a sketch a simple picture. So I'm going to draw just an x and a y axis here. Again, x is going to be your horizontal, y is your vertical. And then in our first situation, when we're talking about the pool, we had a domain and range. Our domain again was between 0 and the time to fill. And then I had a range that was between 0 and 10,000. So again, it's going to be, so we would have something marked there, say at the origin, and then I would be going at a constant rate of change because this hose or whatever I'm using to fill is just turned on, so it's continuously pouring water into it until it's filled. So this would do something like this. At any given moment of time, I have some amount of water in that pool. So that is a continuous type of graph. Okay, versus over, look at the other example here where okay, so if I had 1 table, I would need 4 chairs. If I had 2 tables, I would need 8 chairs. 3 tables would need 12. 4 tables would need 16, 5 would need 20. So this graph looks like this, and it's a series of dots, and this would be an example of a, make sure that looks like a D and not a P, a discrete graph, okay? I can't have 1.2675 tables, and I can't have 3.5 chairs. It is whole numbers or integer values. So this creates a series of dots. I cannot put my finger on this and trace through it all because I will run through areas that are not colored. So I have to put here, pick up, pick up, pick up, and that makes it a discrete graph. This would be continuous. I could put my finger here and just trace it all the way along because any of these values are possible. It could be 1.26 minutes, and it could be some number of gallons, wherever that's at on the graph. So that's the difference between something that is continuous and something that is discrete. Okay, looking at number 6. Again, reasonable domain and range. Okay, so in this one we're asked to analyze the situation, identify again reasonable domain and range. So let's look. So in this first case, a bowler pays $2.75 per game. Okay, so what are we talking about for a domain here? So again, these are your X values. This will be graphed along the horizontal axis, and I can play 0 games, 1 game, 2 games, 3 games, etc. Okay. Again, there's probably some sense of reasonableness there. I can't play 150 games, 200 games, 1,000 games. That probably doesn't make a lot of sense. But essentially, we have these integer values just extending upwards. Okay. And then for the range, we're talking Y values. And again, this would be another example of a discrete graph. I can't play 1.26975 games. I can play 0, 1, 2, 3. And then I have a cost per game, right? 0 games would cost me 0, and then it would be like 275. You can pull up your calculator here, and we can continue to see if my calculator will work. And it did not, so we'll just take 275, and you go ahead and double that. So you get $5.50. And another 275 for the next game, so that's going to be 8 1/4. And then another 275, so 8 1/4 plus another 275 is 11, and then that pattern just continues as well. Okay, so again, a more concrete example of an appropriate domain and range for something like that. If we talk about a car traveling, again, I have gallons of gas and the mileage output. So I've got this input-output concept going on. So I've got X value, my domain. So I put in gas, what makes sense. Well, I could just not fill the tank. I could put in a gallon. I could put in 2 gallons. And I mean, this one really, I can put in 1.26, depends upon how much money I've got in my pocket. I can put in $20 worth of gas, which will get me some amount of gas. It's probably not going to end right at 1, 2, 3, 4 gallons. So this one would probably be better described by saying it's greater than or equal to 0, but then less than or equal to however much the tank holds. Maybe it's a 15-gallon tank, maybe it's a 22-gallon tank, depends on the size of the car, but it's somewhere in between there, and I could have any amount between there. Then your range value would follow suit. Again, this is going to vary depending upon how much gas you get into the car. If I don't fill it and I have no gas in my car, it's not moving real far. I've got 0. And then that would end with however many gallons you put in the car multiplied by 25 miles per gallon. So we could express that as just like gallons times 25, or use parentheses there for whatever the upper limit is. So something like that's going to make sense in this type of case. So the bowler would be an example of a discrete graph, whereas the car traveling would be continuous. Okay, so let's classify whether or not these are one-to-one functions or not. So again, we're looking for exactly one output for every given input. Okay, so we don't want any doubling up. So we look at the x values. So I have a 1, a 5, a 7, and an 8. And then I'm comparing these. Am I getting any duplicate output values? There should be one output for every given input. And again, I have a 2, a 6, a -1, and a 0. Okay, so it looks like I have a unique output for every given input. So this would be a function, and it is a one-to-one function. The way to check that is to create a map. You see that right down below. So I can just do that with my x's and y's, and we can physically draw lines. So if I do that, I just make a little box here. These are my x values. I'm going to put them in 1. I'm going to do them in order 5, 7, and 8. And then I have y value. Maps are very similar to a table, but they don't necessarily have to be arranged in the order here. You can see that down below these will go across. So then I have 2, 6, -1, 0, and then I can either just draw these or I can put them in order. Sometimes it's a better visual. -1, 0, 2, and 6. And then we just construct an arrow, or we draw a line from the x value to the y value. So 1 goes to 2, 5 goes to 6, 7 goes to -1, and then 8 goes to 0. And notice that I don't have any of these going to the same point. Okay, so that's what helps me identify that it is a one-to-one function. So use that same technique and go down, look at number 8. Okay, so again, what I'm looking for is I'm looking to see that there is not two y values for the same x value. That determines if it's a function. Okay, so basically I draw one line from any given x value. So if we're talking about that, let's see. I have, is it a function? So there will be just one line from any x value. That's an easy way to see it. So I have one line, 1, 1, 1. So yes, it is a function. Okay, so then I want to determine, is this a one-to-one function? So then I just want to look and I say, ooh, do I have more than one of these outputs tied to a input? And you can see that I have 2 of these values coming to the 17. 2 of these, 4 and 5, both land at 10. So is this a one-to-one function? No. Okay, so simple as that. Is it a function? I'm looking to make sure I've only got one line extending from these x's. They just go to a y value. There are not 2 y values for a single x. Okay, so it doesn't do something like this, so that 1 goes to 17 and 1 goes to 11. And then for the one-to-one, I'm just checking to see if I have repeated y values. If I have repeated y values, it's not a one-to-one function. Okay, so take a moment, try A and B, pause the video, and then come back and see if we get the same result. All right, let's see how we did. So in this one, again, I'm looking to see, is it a function? Okay, so that means I should only have one line from any given x. Right here, I see that 3 goes to 6 and 3 goes to 7. So this one has already invalidated that. This is not a function, and I don't need to go any further. And then I look over here at the graph and I see just it appears to be a linear equation. It extends in opposite directions forever. I have all of these points. This would be continuous. This is also a function because for any given x, I only have one y value. And it is also a one-to-one. Okay, easy way to check for that is what's called the vertical line test. Talk about that here for just a second. You've heard of it before, and essentially when given a graph, pretty easy check. I just draw these vertical lines, If I can draw them vertical, it is a function. So we can use the function vertical line test. And then if I want to know, is it a one-to-one function on a graph, I can do the horizontal line test. And these pass through that only once. So then this is a one-to-one function. Okay, so on a graph, another way to assess it is I do a vertical line test to check to see if it's a function. Your line should intercept it only at one spot, right there, not at more than one. And then if I want to know if it's one-to-one, I do the horizontal line test, and if it checks there also, it is a one-to-one function. All right, we're going to skip number 10, talk about that in class, and let's look at number 11 then, last one. Margaret has a monthly clothes budget of $50. She maps the amount of money she spends each month to the number of items of clothes she buys. What constraints are there on the domain? So again, we're asked about the domain. Domain is our x. It is our input. And the y value, the range, depends on our domain. So what do we have? So what is our input? What is our independent variable? And then the other depends on it. So she's got a budget of $50. She spends each month to the number of items of clothes she buys. What are the constraints? Well, we've got a couple different things going on here. Okay, if we're looking to identify her domain, we are talking about x values that would be between 0 and then up to however many items or clothes that she buys per month. And then we've got this y value, this range, or the output, or the dependent variable. And this is going to vary. She can spend no money, or she could spend a maximum. She's constrained by her $50 on the upper end. So that's all that she has. So whatever she's doing here in terms of the items of clothing that she's buying, she's constrained by the $50 that she has budgeted each month. Okay, so that's kind of what we're looking at here in this type of problem. At this point, we just really want to understand it, and in the next sections, we'll take this, we can develop some values for it, and then we can look to graph it. But for right now, her domain that makes sense, and again, this would be something that would be a discrete function or a discrete graph, because I cannot buy 1.267 items of clothing. I can buy none, 1, 2, 3, up until whatever I'm constrained by, $50 worth for the month, and then we could plot those individual points along the graph. So again, something that would be in the first quadrant, I could buy none, I could buy 1, maybe it's a cheaper clothing item, the second one maybe is pretty expensive, and then I could buy a third. And so we can just have some sort of graph like this that plots out, but you will have independent points representing each item she buys and the total cost. So it wouldn't be something that is continuous over a line where any point on that line is one of the outputs. Okay. If you have any questions, bring them tomorrow. We'll discuss them in class, and then we'll get some practice.